let's see. Any objections to talking about characters? We use them every day. I think Panda is particularly good at them. But most of the time we don't have to think too much about what goes on the inside. And the first question that comes to mind is, what is a character? And I had a hard time answering that last time. I thought about it a little bit more. I guess in the Panda sense, a character is any model animated character converted from a animation package, such as soft knowledge or Maya or Alias. Typically a single scene in that package, which usually corresponds to a character, but it might be a prop or some single piece of some single model. There are exceptions. In the case of the tunes, there are actually 3 characters each, because we had to have these split body tunes to be able to switch in and out heads and feet and torsos and stuff like that. We only did that because we had to. If we had a druthers, we would make the tunes be just one big character. So at the first level, a character starts off in some package, in Maya, for instance, and it consists of a skeleton, and of course it looks something like this, but basic idea of what a stick figure skeleton in Maya might look like. There's a skeleton in Maya, for instance, and a series of polygons or whatever the animators created is attached to the skeletons. So the modeler is responsible for creating the character, creates a bunch of polygons, and associates each polygon with one or more joints. So that as he animates the character, the polygons move with the joints. Typically, there's either hard scanning or soft scanning. In hard scanning, the polygons might be parented directly to the joint, which is pretty much what we used to with the scene graph. In soft scanning, a polygon could actually share vertices between different joints. There might be some vertices in this joint, some vertices in another joint. Furthermore, each vertex might not be in entirely one joint or another. Some individual vertices might be partially in one joint, partially in another. And that's how you get nice smooth effects of elbows and such like that.
And they can tweak how much they're influenced by each of the ones that they're associated.
And nowadays, all these animation packages have nice tools where you can very easily, at least relatively easily, set up the skinning ratio. You should just say, basically, here's my polygons, here's the skeleton, click, boom, it's all done. So I'm told. So then at some point we run Maya to egg, or soft to egg, or max to egg, or whatever the heck we're running, and we produce an egg file. And actually we have typically at least 2 egg files for a character, because we have one for the model. So let's say we have sometimes we call it 0. I'm not sure why we call it 0. Just by convention, the 0 is often the name of the first model. And then we might have a different egg file for each animation. Say, for instance, it's got a swimming animation. Now, the model file and the animation file are totally unrelated. Well, I mean, they're related, but they're totally different kinds of files. The model file has just polygons and joints. Reflects basically this hierarchy. And the animation file just has a table of data. Table of frames, matrix positions, 1 per joint per frame. Now, they don't have to be different egg files. It's possible for these to be the same egg file. But typically, we make them separate egg files because we have multiple animations. We want to be able to mix and match particular animations we want to play. And a lot of times we can have, if we have the same skeleton, of course, we can play multiple animations in one skeleton. So there is, the representation in egg is worth talking about on its own. It's somewhat different from the representation within Panda. So once we load it in Panda, it gets converted into a different form altogether. And I'll come back to that, or I'll come back to the egg representation. Once we load it into Panda, we have a character node, ultimately, is at the top of the scene graph. if we would just look at it, he's probably just got one child, which is a geom node. Once we load it up, it's not doesn't look like very much on the outside in the scene grid. Sometimes, depending on how we what flags we have in the egg file, he might have multiple geom nodes. But typically, it's just like this. There's a character and probably just one geom node. But what's actually, we actually have some controls on the character. Once you get to the character node, we can then load up the animation. So this would be the model file. For instance, tune0.egg. Now it's just tune0. We just loaded the egg file and got this character node. If we load the anim file, we get an anim bundle. Actually, it's an anim bundle node. And this will be tune swim. So we can take the anim bundle, which is just a single node, but inside this anim bundle node is stored all the animation data that we loaded from the swim animation. And we can call the character mechanism to bind the animation to the character and start to play it. And then the character seems to start swimming. So the geom node, the vertices are actually changing. Now there's a lot that's going on in the background. And I'll come back to that in a minute. On top of that, we've got another interface, which is the actor interface. And this is what you most commonly use to load a character. This is written up in Python. This is in a direct interface. So actor.py is a nice friendly interface. You just basically say, give me an actor, and you give it a dictionary for its parameter, and it's something like tune0.
Yeah, it's just the model and then a list of the
Yeah, that's right. Actually, it is a dictionary because it's a dictionary of names to model names. So swim : tune swim.egg, for instance. And you might give it multiple animations, and you name each animation according to whatever name you want to refer to it in the show code, which may or may not be related to the actual name of the file. Often they're the same, they don't have to be. And now actor is actually a node path. So you can take your actor and reparent it wherever you like. And it's actually reparenting the character code. And now you just play the animation. You say actor.play tune0, or actually, I'm sorry, actor.play swim, and your tune starts playing swim animation. What's actually happening is the actor is then binding the character, getting the anim bundle off the swim, binding onto the onto the character, and calling the character play. So we've got at least 3 or 4 layers of conversions going on here, and they're all really completely different interfaces. But we can talk about each of them at least enough to get us a fundamental understanding of how they all work. Everybody with me so far? Okay, let's get back to the egg file. Normally in just an egg model file, a static model file, we just have basically polygons. Polygons maybe with a hierarchy, a bunch of groups to group them all together. And this closely corresponds to the scene graph as we load in the egg file. So an egg file is a collection of nested groups. You can look at an egg file, it's all text. Everybody knows this. If you open up an egg file and look at it, you just see a collection of nested group nodes. And within the group nodes, you might see a list of polygons and vertices, vertex pools, and stuff like that. When you load up a static egg file, it creates a bunch of polygons, basically turns any group that contains a bunch of polygons into a geom node, and any other group that contains other groups into just a big Panda node, and creates a big scene graph that way. Character, when it detects the character file is very similar to a static model file, except that it has a hierarchy of joints, and it also has, at the beginning of the character, it has one entry called dart.
We still use that.
We still use dart. For historical reasons, the dart indicates the beginning of a character, and that starts. I don't want to go into why it's called dart, but the dart flag indicates a character, and then we also have a hierarchy of joints. So when the egg loader sees the dart flag, then instead of creating a hierarchy of nodes matching what the egg file has, it throws them all into one geom node. All the polygons go into one geom node, and it creates a character object that references into the geom. The reason it creates just one geom node for a character is because usually in a character you really don't need that hierarchy. The hierarchy is usually there as a modeling convenience, or representing an entire scene, it's helpful. You may want to be able to go in and manipulate the scene from a show character point of view. But with the characters, we typically consider them atomic objects. There are exceptions. There are times when you actually do want to manipulate individual objects, and so we provided the facility to split those out, as I mentioned obliquely a few minutes ago. But for the most part, you probably don't. So the fact that there are individual groups and stuff is really only for the modeler's advantage and not for the show coders. And there's a performance benefit to having it just in one node.
So that's how we separate it out to have like the waste node to parent things to or something.
Yeah, there are two kinds of ways we flag nodes for being separate. One is such that the node itself is animated, and that allows us to parent things like a pie into the tune stand. And the other is where the node may not be animated, still the vertices are animated, but the vertices are separate from the other vertices so that we can color them. So for instance, we color the tune's head, his face, and his arms differently from the way we color his torso, which has a texture flag to it. So in the case of the tune, we have to pull out the legs and the arms and the torso and the head as a separate node so we can get different colors. Actually, because we colored potentially the legs and the arms differently colored, they have to be separate nodes each. And the torso has to be a separate node because it gets a shirt texture. But they all just mean ordinary geom nodes. Still, within the geom node, it's just the vertices that are animating. It's not the geom node itself in those cases. That's different from, there's a separate node which is the hand, left hand and right hand. And in this node, there actually aren't any vertices. It's just an empty Panda node. But this node itself is animating transform as the character animates, so that there's always a node that represents what the hand position is, so that we can put a pie or a salsa file into it, parent it into this hand node, and it shows up in the tune's hand.
So that hand node is being actually manipulated by the animation data.
Yes, and the difference is the DCS flag.
Is that true also of the waist?
The waist is actually a separate character, because we stop the character at the leg, the top of the legs, and then we parent the torso on top of the legs. So that's a little bit of a special case, and I can talk about that too, but let me get about
Probably not bad.
Wait, we'll talk about the fundamental character stuff first. Okay. Now, I've mentioned obliquely that there is a difference between just the basic behavior of just getting one big geom node or getting separate geom nodes, and also getting an animated node. And the difference, well, let's see. You could edit the egg file and do it by hand. If you put a DCS flag into the egg file or into a particular joint, that will guarantee that joint shows up as a node by its own name. And there won't necessarily be any geometry in that node. There might be. If it happens to be geometry that's hard to that joint, then the character code will realize that and just parent it to that joint, because that's the easiest thing to do. But if you did not expose a joint, and there's geometry hard scheme to that geometry would still be hidden within the geom node, and the character would animate the vertices to that geometry every time. Let's see, I've kind of glossed over the difference between animating vertices and animating a node. Suppose we had geometry parented to this node. If this were a rigid geometry that does not animate, the vertices remain fixed every frame, which is the way we normally do with scene graph animation. Normally we think of vertices as just remaining fixed. It would still inherit whatever transform the hand has. So if there was some object that in the character happened to be a static object that was always parented to the hand, and we did happen to expose the hand geometry, then it would create a separate geom node, a static geom node for that hand geometry, and parent it to the hand node. And then it just take advantage of the existing DCS to move that piece of geometry around. But most of the time, if we're not exposing anything, it all becomes dynamic geometry. Ends up in here, where the CPU has to calculate the vertices every frame instead of messing with any DCSs. So every frame, the CPU, rather than the graphics byte, calculates where each vertex is according to the character's animated position, and adjusts the vertices in here so that the character just animates without having to have any transforms going on there. The reason we do that is because there's so much soft typically. Nowadays, supposedly the graphics cards have support for doing soft scanning in the pipe. I haven't looked at that interface, but I'm not sure how good it is. We haven't tried that. Okay. Let's see, have I So I've talked about how the egg file becomes a character, at least how the geom nodes become parented to the scene. But we need to talk about what the character actually is. So I can talk about how the joints become part of the character. A character node actually is a part bundle node. In class hierarchy, it inherits from part bundle node. So a character is just a specialization of that. And a part bundle node, the part bundle node is really just an excuse to hold a pointer to a part bundle. Part bundle is the actual character. And the part bundle is actually the root of a hierarchy of joints, which have nothing to do with necessarily what's in the scene gun. This is a separate hierarchy. But for a given character, suppose this character, we have, I've drawn some joints in some strange correlation. Let me draw joints as circles because I've drawn that node as spheres. So at the root, we've got the part bundle. And he looks like he's got a shoulder joint, and looks like he's got two arm joints. And under here we've got another joint, and then two leg joints. So this is the fundamental hierarchy of the character inside the character node. This is actually just pointed to by the character node. Part bundle is the only special interface you've got on part bundle node that you didn't have on Panda node is get bundle. If you ask it for the get bundle, it returns the part bundle, which is the root of your joint hierarchy. And each of these nodes has a name, which will be the same name that we'll have in the original Maya file, which makes it easy to find a particular joint. And the joint really doesn't have that much more going for it. It's just a name, a position within a hierarchy, and one initial transform byte, the initial joint angle of the joint. There's also a list of morph transforms, which we don't really use these days in Toontown. We have used them in the past. We probably will use them again if we get into character animation in detail. I'll set those aside for now, but they're kind of similar to joints. They're called blend shapes sometimes. They're another way of doing animation. Usually, if you particularly want to do facial animation, you use a lot of blend shapes. But the joint hierarchy is where we get most of the animation from. Now, in the anim bundle node, coincidentally, all you find is a pointer to an anim bundle, which, as we all know, is colored in red. And anim bundle, by definition, has exactly the same hierarchy as its corresponding part bundle. Has the same hierarchy and the same names for each node, so that the anim bundle corresponds node for node with the part bundle. And to be complete, there's also all the morphs. So the anim bundle is actually a table of joint angles per frame. Now, in each node, we actually have some real data. There's for a given frame, for a given node, which corresponds to a joint, there'll be a table of however many frames of animation you've got, that many matrix transforms. They all have to have the same number of transforms. If they don't, that's an error. And it happens sometimes that we have that error. So, when you take the part bundle and bind it to the anim bundle, it walks through the both hierarchies, matches them up name by name, and associates the joint with the table of animations that will be binding. And the result of binding a part bundle with an anim bundle is called an anim control. That's what you get when you take a part bundle and bind an anim bundle. The anim control is what you use to play the animation. So the actual interface to play an animation is on the anim control. You take the anim control called play, stop, loop, ping pong, whatever, all set your play rate. All the control to the animation is on the anim control. When you take your anim control and play, it immediately, by default, stops whatever other anim controls you may have had playing and starts playing that one. And your joints position to the first frame of the animation and subsequently will automatically position to its later frames. And of course, when a joint positions to a particular frame, that means that all the vertices associated with the character will be recomputed according to where that joint's position is. Yes?
Are the anim bundle frames, are they all from like a zero position? Does the character animate from the zero position every frame, or is it deltas?
They're from the zero position. Everything. That is relative to the parent. There is a normally inherited hierarchy. But yeah, it's always an absolute position of this particular frame, of this particular node, relative only to the node's parent, not to any delay in time. So you can very easily position to any frame in the animation without regards to what was playing before. That's a good question. Now, it's also possible to have, as I mentioned before, we can have multiple animations. You may have a tune breathe, for instance, a tune neutral. And if you bind that one, you get a different anim control. Now we've got two anim controls on the same character. That's fine. We can play this one, he starts breathing. We play this one, he stops breathing and starts swimming. We can also do real-time blending, where we have, say, 10% of this one playing and 90% of this one playing. That's not on by default because it's expensive. You don't want to turn it on without meaning to. But you can. And if you turn it on, then you just specify the weight of to each anim control that you want to play. You start playing all the anim controls you cleared off. Once you turn it on, you have to be careful that you do, in fact, stop the other anim controls, because otherwise they won't stop automatically, and you may be playing characters with animations you don't intend to be playing. Now, that's well. And you can have any number of anim controls playing at once. Yes.
Can you have? I guess you could, but is there any examples of an anim control that's completely procedural and not table-driven, and can you blend that with another anim control?
You could in principle. It's designed to allow that.
In fact, when we originally wrote all this stuff, that was one of the, this is way back when we were trying to control from mouse control an arm or something.
Yes, we had the carpet, the darn carpet we had to control with the carpet controls. So those were blend shapes, those are morphs. So we had to have procedural ways to control the morphs on the carpet. So we carried forward that design. Although the actual code is not supported right now, there's a place for it.
When does the anim bundle get loaded into memory? Is that the first time you try to play it?
So that's a good question. That has several answers. Once you have an anim bundle, it's already been loaded. So it already exists in memory. There's already a big table of joint angles in memory. When you bind it to the part bundle, it gives you an anim control, which it creates on the fly. But that's a relatively lightweight thing.
And these anim controls, they don't have to have the same number of frames, like to merge
Correct.
them.
If you want to blend two anim controls, that's fine. It doesn't matter how many frames they have, particularly if they're both looping. In fact, I did a little bit of this in the early fishing interface. I'm not sure if we're still doing it in the new fishing interface. But we had an animation that showed the tune holding this fishing pole out. But it was just a freeze frame animation because it was really just one animation in the whole series. I wanted to show I'm standing there and maybe normally. So I had to blend the breathe animation, which is the tune standing like this, with the holding the fishing pole animation, which is the freeze frame like this. So I had one frame, one anim control, and 24 frames looping on the other anim control. Yeah, that actually looks pretty cool. But the serious question: when does the anim bundle get loaded? The actor actually manages delayed loading of the model files, so the animation files. So in the case of the actor, if we're using the actor interface, just creating the actor does not load any of the animations by default. Until the first time you reference a particular animation. Then the first time you call swim, you say play swim, then it's going to load the swim file if it hasn't been loaded already, which creates the anim bundle. It'll bind the anim bundle to the part bundle, save the anim control, and then call play on the anim control. That's what the actor does.
Is that pretty heavyweight loading in anim bundle? I guess I've noticed pauses with like the animation hasn't been loaded.
It's a hit to disk. So it's as heavyweight as that is, which can be pretty heavy. But it's not too bad on the local disk, and we get away with doing that on Toontown because when you do you're loading from the local disk, it loads pretty quick. So you're running around. It's the first time you push, walk forward, your train has to load the run animation. The first time you push walk left, your train has to load the walk animation. The first time you jump into battle, you have to load all these other animations that have to do with battles. And yeah, there's some hit, but it's not as bad as the hit for loading the model itself, seems to be. And there's a big hit that we get for just creating all these Python objects for the suits and things like that. Seems to well overwhelm the cost for actually loading that in.
It's also nice to not have such a hit at the zone.
Yeah,
There's
that's
something
true.
that was worse and got better as things got.
Was there any reason why you didn't like sort of try to bundle the animation together and load it at once and then the sequence from memory?
Sure. Our first design had we loaded all the animations we'd ever used when we come in the game. We had the loading bar that comes up, the loading machine down, we load everything up right then. And biggest problem there, memory bloat. Animations are pretty large, especially when you load all of them. We got probably hundreds of animations in Toontown, especially consider all the battle animations. Also, it is a pretty a big delay waiting for all that stuff to load. It's nice to kind of spread that out. And a lot of those animations you're never going to see. I mean, if
Yeah.
I'm going to run into Toontown just to go to my estate and see what I got in my catalog, I don't care about loading Python. So that's one reason not to load everything up front.
Do you think it's worth compressing that at all? Like the animation?
We compress them on disk for download. We don't compress them in memory right now. We could talk about that.
You probably don't have enough joints to make it really necessary right now.
Well, the animation table is pretty big, but still, it seems to be dwarfed by whatever the heck it is the DirectX is doing. So we would get some benefit from doing that, but it's not clear that we'd be a real big win.
How big are these sending files usually?
Well, you can work it out. We have typically 24 frames per second. One frame is one matrix for a particular joint, and a matrix is, well, actually, it's not quite a whole matrix. We typically store up to 9 floats.
Yeah. Rotation and the translation.
Rotation, translation, scale.
And the scale.
Actually, it could be up to as many as 12 floats because we now store shear in there too, but we only store whatever parts we actually need. So probably the average number of floats we're storing on any given frame is closer to 6, because many joints only have rotation and translation. Not all joints have scale. So
6 times 24 times the number of seconds times the number of joints.
yeah, 6 times 24 times seconds times joints times the number of bytes per float, which is 4. So
Plus a little.
what's that?
Plus a little overhead.
Yeah, a little bit of everything.
Can we-
Not a whole lot in the big scale things. So it comes up to these megabytes for a few seconds of animation, or for like 30 seconds of animation is several megabytes.
Have we thought about like instead of using float, like use a fixed integer or something? Or?
Tried that once.
That looks
Looks
so
terrible.
nice, yeah.
It's absolutely terrible.
It turns out animation it's like faces, humans
Yeah.
are wired to recognize continuous silhouette movements and things like that.
I guess you have a combination of large movements and fine movements. That's where fixed point just falls apart.
Yeah, exactly. Now we found out that compressing for download, compressing and storing on disk, we do a pretty effective compression, which is very similar to what JPEG does. It involves doing a Fourier conversion on the animation, and so you end up storing just a combination of sine waves to make up what the actual animation is. And since animations tend to be natural shape motions, it works pretty well. There are some kinds of animations that just breaks down on totally, and then we store those as compressed. But for the most part, storing them with the JPEG type compression works pretty well, and you get similar results to JPEG, 5:1 typically storage compression ratio. Actually, that's worst case. Typically, you get much better than 5:1. And if we needed to, we could probably do that on the fly, the decompression on the fly for that. I'm not sure if it's worth the CPU or anything for that. Other things we've talked about, people who are familiar with other graphics engines always ask why we store every frame. Why don't we just have keyframes and interpolate between them? And it's a fine question, and the answer is because we don't need to. Because we get a much better result from having every frame, because this is exactly what the animator had in mind. Our animators are particularly fussy about it, because they have it in the past.
I can be more specific on that too, like at least from the Bob Taylor days. It's all about right before the stop. It's like the wind up. So you have slow, 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 and then something really important happens quickly. So you if you interpolate from the wrong keyframes, not all keyframes are equal. I guess is the point, right?
Yeah. Now we could try to do the right thing. I mean, there are typically keyframes in here, and we could try to convert the keyframes out of Maya and represent them all in our format. We have to be careful that we also get all the constraints out of Maya and everything else that the animators are depending on to get the keyframes out. And we could probably make that work with some caveats. There'd be a lot more limitations to what the animators can do. Right now, the animators can pretty much do anything they like because we're just getting out the joint animation.
We're
Doesn't matter.
sampling the position
Yeah.
between.
We basically ask Maya, hey, play the animation, and every time we look at we ask Maya, okay, what does the animation look like at this frame? Okay, what does it look like at this frame? Whatever Maya wants to do to keep that, we're happy with that. So they do all sorts of crazy things. They constrain pieces to other pieces. They animate those constraints. They I don't know. They put equations, sine waves, and things like that sometimes. And if we wanted to represent all that in our format, we'd have quite a large amount of lit to represent all that. But they probably wouldn't mind restricting that a little bit, and we could get away with that. But
Isn't there a middle ground where you'd be sampling the position at strategic points
Yes.
in the animation and interpolating between those?
Right.
So it's not a constant rate of.
yeah, we
sampling.
could try to be clever and do some good sampling. And there are other graphics engines that do that. We haven't really had a need to. The memory blade isn't really the big issue right now. And another advantage too is this plays a lot faster. CPU is actually our biggest limitation. Well, one of the biggest ones actually. But it's the darn DirectX stuff that's the biggest.
The DirectX, have we ever figured out what that is? Are they just shadowing all of our
Yeah. that's
data
pretty
basically?
much-
Which is what OpenGL did on the SGI thing.
Yeah. Yeah, what are you gonna do? I mean, the graphics driver is free to do whatever it wants to do with it, except you give them. It's not DirectX per se. It's typically the graphics driver. I shouldn't blame DirectX, but it also the same thing.
Can we throw ours out since they're keeping it happy?
No.
You use the remote storage for our.
We actually do that with the textures. We load up the textures and we send it down to the graphics driver, and then we throw our texture copy away. But that makes us sad whenever we re-enter the zone and have to load the texture again. Okay. Anyway. I lost track of where I was. So we have, the bottom line is our characters right now are just a table of rigid joint animations, a table of joints per frame. It doesn't have to be that way. If there were a demand for it, we would probably be more inclined to try to be smarter about it with keyframes, sample keyframes, whatever we needed to do to make it work. We're clever guys, we could probably do that.
Especially for like people working more or something like that.
Oh yeah. cell phone games we may not be able to
Yeah.
do.
Yeah, particularly now that the CPUs are getting a lot faster,
Yeah.
we can try to do a lot more in the CPU. I mean, last layer we couldn't do real-time blending. So it was really out of the question. And now our CPUs are not so bad that we can do that. Okay.
What about IK? What's our plan for?
Okay, that's another good question. That comes up from time to time. We don't have it. We could, in principle, because we have the hierarchy of joints, which is the first part of IK. IK, or if you're not familiar with it, it's called inverse kinematics, and it basically is just applying physics to your joint hierarchy. It says, if given that my hand wants to be here, how do I adjust every angle on my elbow to make the hand be here?
And it's mostly just really simple physics. Like you can't extend your arm longer than the sum of this part and that part.
Right.
That sort of.
Yes, simple rules of that. You have to set up constraints like that. You have to set up rules like, well, your elbows don't bend backwards, things like that.
But it's not taking like mass and velocity.
It could. A good IK system would do that. A good IK system would, some games use this sort of thing for having people running upstairs and things like that. We don't. Everything we have is strictly from the animator. We have very little generated animation.
Would we use the same kind of IK that they use to animate in the first place? Would we translate that, or would we have our own?
It's a good question. Haven't thought about that too much. My gut would be we'd have to do something much simpler than what Maya can do, because Maya is designed to be nominal time. And it has a lot of very sophisticated stuff in there.
But wouldn't we want the animators to set the constraints for us? Like maybe bake out
Yes.
a version of what they use.
Ideally, we'd want to be able to translate from whatever MI constraints we have into our running constraint system and apply the IK directly to the similar structure. Not sure what the implications of that are. Again, there's some limitations on the sorts of things we could do up here.
Yeah, I mean, I was talking to Burdoff about this a long time ago when we were trying to use his IK thing. He never really, I don't think he had a very good picture of how that would work.
Yeah, it's not an easy question. And again, it's something that's possible. I'm sure we can solve it. Hasn't been any reason to right now. One of the strengths of Toontown and the Gear Studio in general is the quality of our animation. And that generally comes out of the fact that everything is animated directly by an animator. I mean, it's comes down to Pixar quality, right? If you have, it's the difference between a Pixar film and say Final Fantasy, which has some keyframe animation, it's a lot of motion capture, and a lot of people just stitching stuff in between. It came out okay, but you could do a lot better. So, as long as we want to have cinematic quality animation, then this is really the only way to go. But if we want to have some compromise between cinematic quality animation and interaction with a dynamic environment, you have to be a little more clever. But we don't have that right now. Okay. I think that's a pretty good high-level picture.
Could you maybe describe what we're doing in Toontown with the structure of the characters?
The
Why
Toontown
they're-
avatars.
Yes, the tunes are indeed a monster of this structure. Is everybody happy with what we've done so far?
I just had a little bit of question, I'll ask you later about the part one with geometries, the hand stuff and the additional geometries. I'll ask you a little bit details later on that. Like I just wanted to know like what is the purpose and how it is used.
What is the part bundle now?
So no, the
Oh, the
so
part bundle, okay.
everything of the part bundle could be in geom node, and then you sometimes separate it.
Oh, I'm sorry. Yes. Okay. The geom node is really all it stores is vertices. It's a table of vertices for triangle strips, trifans, individual triangles, and stuff like that. The part bundle all it stores is joints.
Okay.
That's the difference between the two. The part bundle is really a hierarchy of joints, and each joint, its only purpose is to store a particular angle at a given time. There's another character, there's another logic, which is actually in the character class, which I've erased here, but it's inherits from part bundle node. In the character class, knows to scan through the part bundle. Actually, this is worth pointing out too. The character actually animates when the node is rendered. This has an advantage that if the character is off screen or outside of your viewing frustum,
You're going to have to animate it.
right, it doesn't pay the cost for animating the vertices.
Okay.
But the
Well, don't you have to know, like, I guess you're culling.
You don't animate outside your bounding sphere.
yes, that's the limitation. If the
So
vertices,
if the animation would put my hand visible though, it's just not going to show
Yeah.
up.
yeah, that's a problem with the current system. If the vertices happen to move outside the bounding sphere, which is computed at load time, then you've got problems. Potential problems because the character might be culled incorrectly. He might appear when he's not supposed to be
The
there.
bounding sphere is computed by applying all the animations that you got at the time.
No, it would be nice if it did that. But in
Just the
fact,
first pose.
yeah, just the
zero
first pose, the
pose.
neutral pose. And the intended design is for the bounding sphere to actually animate also. But that functionality just hasn't made it into the player yet. So typically what we do is when we have a character that we know is going to animate out of the bounding sphere, we either give it a very large bounding sphere by hand, or we just take the bounding sphere off and say, okay, you're always rendered. And that works. Usually it's only a very few narrow cases that the character does animate outside the bounding sphere.
Sorry. I interrupted.
No, that's a good point. Yeah, and now you back up another stack. Since the character is animated at the time that it was rendered, it has advantages for performance, and also that disadvantage of the bounding sphere problem. And another disadvantage is, well, it makes the cult traversal take a little bit longer because the cult traversal actually has to do the rendering. And our friends at CMU discovered another disadvantage because of the animation of the character, or the camera actually animated. We had a case where the camera was parented down here. And in that case, what happens is the character animates during the cult traversal, which is very strange because the camera transformed is used during the cult traversal to figure out what's being culled. So we had problems with some things were being pulled at different times, and some things were showing up in different positions. They're very strange behavior.
Because the camera was moving during the.
Right, so we transformed through some of the nodes, transformed some of the nodes according to where the camera is, then moved the camera, and transformed some more nodes according to where the camera is. And yeah, so things ended up in different points of the scene. And the effect was that some objects were shaking. And it wasn't the objects that were attached to the camera that were shaking. It was very strange.
Oh, because the camera's shaking.
Right, but
Sort of.
yeah.
Mid-frame, mid-render.
Yeah. So-
It's like a dual exposure picture.
So that's an unexpected consequence of having the character do the animation at full time. But there's an alternative, and we solved that problem by just having the character explicitly force its animation when you set its frame. So you can do that. There's a method on character to say, okay, render now, real animated.
Could you maybe extract the current transform of the camera and just say, okay, that's what we're going to use for the camera? from now on?
Yeah, in fact, we do that most of the time, but there's a few exceptions, and there's exceptions for this. Basically, when I read the culture verse, I hadn't thought of the camera moving during the culture verse. Just didn't occur to me. Yeah, there are other good solutions for that. But anyway, okay. But this does burn you every once in a while, the fact that the character doesn't animate until it's actually drawn. And people get confused by that, and so it's good to keep in mind. Alright, now I was actually answering a different question, which was what's in the part bundle? And why is it different from a geometry? At any given frame, the part bundle, at any given time, each joint just has basically a transform. Basically a transform matrix for each joint. The character has a separate table of all the vertices in the character and the pointers to the geom nodes, and knows about the part bundles and knows what weight assignment is each vertex to each joint. So the character tells the part bundle to apply its transforms to all the joints for this frame, and then looks up each vertex in the appropriate place and applies the transforms to the vertex and modifies the geom node. Now, I guess we could put this logic in the geom node. That would make the geom nodes very big and heavy, particularly because we use geom nodes for more than just characters. I mean, most of the geometry in the world is geom nodes, but it's mostly static. So there's no need for the geom node to have all that smarts about joint angles and dynamic vertices and stuff like that. It makes more sense to have it only in the node that's using it, which is a character node. But it does mean there is an implicit association between the character and its geom node. And if you were to take this geom node and reparent it somewhere else, it would confuse the character. I think what happened is, well, I'm not sure. It might continue to animate this geom node even though it's not parented to it. It might stop animating, but it would certainly confuse it.
Did we ever implement vertex lists or vertex buffers?
Vertex buffers, no.
Wouldn't that be difficult? I mean, in the character case, it'd be difficult, right?
Right.
Because that implies that they're cached
Yes, there are in fact.
on the hardware, right?
There are in fact two different kinds of geoms inside the geom node. There is dynamic and static geoms. So the character actually has dynamic geoms, which are almost the same as static geoms, but they have another level of indirection.
So they wouldn't get buffered.
Right, we would just not buffer those. Okay. Does that help
Yeah.
your question a little bit? We can talk more about that if you'd like more. Okay. Now hopping back up to Darren, you had.
The structure of the tunes.
Yes, the tune tones.
How exactly are those?
Okay.
In 5 minutes. Just look at the file, Darren.
So I already said that actor was a layer on character, and usually an actor is 1-to-1, one actor for one character. That's not the case in the tunes. The actor is actually 9 characters in the case of the tunes. So, what do we have? Let's see. Let's draw a picture of what we have looks like. We have legs. That's a character. On top of that, we have a torso. A different character. And we also have a head. And particularly if he's a dog, he's got animating ears. The other heads, fortunately, don't animate. So they're not necessarily characters. But the dog ears do. So that's at least 3 characters right there. Now, what does the scene graph look like? At the top, we have the legs. And he's got the geom node for his legs. Let's love that. Yeah. Okay? Where's it good? Now, he's also got a node that we exposed by putting a DCS flag in the joint. There are other ways to expose joints, by the way. The egg opchar utility is a command line utility that we normally use during the building process. We just tell it which joints we're not to expose, and it exposes all the joints for game. But I won't go into how that all works right now. But anyway, he's got a joint which is called joint to hip. That's actually, if you look in the joint hierarchy of the legs, the joint hierarchy actually starts at the bottom.
Well, the root of the joint hierarchy isn't the root at the waist?
No, the root is normally at the waist. In the case of the tunes, it's
It's at the feet.
no, maybe not. Yeah, you might be right. Maybe it's at the waist. I'm not sure. Let's say it is. So he's got a few joints for his knees and his feet. Probably a few more than that, but that's the point. And this top one is called to hip. So we expose this joint in the way with the DCS flag, so that it becomes a Panda node, which is animating. That means we can parent more stuff to this node. How about that? We've got a torso. I should draw this in the same color, but too bad. So we parent the torso to the hip. Okay, same story. We've got the geom for the torso, and incidentally the hand and the other things we talked about. And at the top you've got a neck, which of course corresponds to the top node up here. This has been exposed as a DCS. Then we parent the head to that. Okay? Not so bad, right? And in this picture, this guy is a character node, this guy is a character node, and this guy's a character node. These are just geom nodes, ordinary geom nodes, and these are ordinary Panda nodes that have to be animated by the character. Now, all that is under an LED node.
There's 3 of those.
Right. So we actually got, basically 3 copies of the same thing, one for each level.
Oh, incidentally, Dave, when we were talking about the parenting to the hands, these all been fixed. No, I found a couple.
Oh yeah, I know. No, it hasn't been. We fixed it in the sense that we've got a node now that you can parent to, just one node that you can parent a pi to. But there's a lot of code that parents 2 pies.
Yeah, the smooch attack.
Yeah.
It actually has 2. It doesn't care about the third level.
Oh, yeah. See, that's a problem.
Oh, it was actually intentional. I think we did it because we're like, far away, hey, don't worry about it.
Yeah.
Don't worry about that crap.
Yeah.
Just have this handy.
Right, so basically another copy of this hierarchy is duplicated for each LOD. And the LOD node, as you remember, is a special node with the property that only one of his children renders, and all of the hierarchy in that. Now the actor actually is a node path. What color is a node path? Same node path as orange. Or red. Okay. The actor is a node path that references the LED node. I think the top node is actually the LED node. It might be a node above that, but not the same thing. And the actor has all the interfaces that when we say play neutral, it finds all the pieces of all the tunes, all the joints, or all the torsos, all the legs, all the heads, and plays a neutral animation on all of them.
How does it know to only animate the correct LED? Or it animates all of them?
The actor doesn't do that. Remember, the character has a magic that it actually only animates when it's visible. So,
Okay.
by the virtue of the fact that
So it just often happens as if it were called.
yeah,
It
in fact,
assumes.
basically, yeah, the LED you can think of as a color. It calls 2 out of the 3 children.
And that happens during the call traversal. The
Right.
LED, that's when the LED is in effect.
Yeah, the LED switches on that and it's ultraversal also. So right, all the actor does is it knows about the set of characters that it's got, and it has a big table of table of animations. And when you ask the animation by name, it looks for the animation, sees if it's been loaded or not. If it hasn't been loaded, it loads it for all the characters, and then it binds it to all the characters to get an anim control.
And it's
Or actually gets 9 anim controls.
and all it knows is this is all of the characters that I have, and all of them are going to accept the same animation.
Yeah, more or less.
So I'll just go through the list and say, hey, everybody play this.
More or less. It does have a hierarchy. You can ask it for a torso node. You can say, give me all the torsos, for instance, something like that. But yeah, for the most part, it just goes for its entire list. Maybe say play.
As simple as that.
When you said 9 characters, it's like these are like 3 characters on each LOD.
Yeah, 3 animation utility. Essentially.
And does each have its own animation? Is the torso in one LOD a separate animation from the torso in another LOD because there's different joints? Or
Actually, no. They can play the same animations, but they do get a different anim control. They have the same. They have the same skeletal hierarchy. So you take the animation for neutral, for instance. Actually, there'll be one animation for neutral legs, one animation for neutral torso, and neutral head. So 3 animations for neutral. And you take your neutral legs and apply that same animation to your 3 legs, and that gives you 3 different anim controls. And then you call play on each of those 3 anim controls. And now
so
you
the
have three
different row polygon skinned on them, but they'll have the same skeleton.
Right. And of course, we also have accurate interval if we want to go somewhere else. But we don't. We're out of time, so that's. I think we're done with that. Okay. Thank you.
God, this wild.